Hi everybody, welcome to this lecture on Boolean formulas and equations part 2. And we've already looked to some extent at these sorts of formulas and equations in the previous lectures that have addressed chapter 2 in P&G, or the Black Book. And today we're focusing on section 2.6 entitled Predicates and Quantifiers. So a proposition is simply a formula that is either true or false. And what's defined as a predicate is a set of propositions. And a predicate is a collection of propositions indexed by a set known as the universe of discourse. And if we define P as a predicate and X as an element from the universe of discourse, then what we call P of X is the proposition selected from the predicate by the index X. The term set actually has a checkered history in mathematics. There are several cited flaws of the definition of what we call the set. But fortunately, the sets that we discuss here have a definite mechanism to determine whether an element belongs or not. And the universe of discourse can be thought of as a set. Examples of such sets include a collection of source code in a compiled or interpreted computer language, and potentially also the natural numbers, which are positive integers, sometimes including 0, and sometimes not including 0. So if we're given the equation or the formula P of x1 and P of x2 and P of x3 and P of x4, we might kind of scratch our heads and try to ponder when the formula is true. And this formula is true when all the propositions in the formula are true. And since we're talking about a logical AND, the overall formula is only true when each proposition is also true. And writing a formula like this is okay when the predicate only consists of a handful of propositions. With a large predicate, it becomes difficult to write a formula like this. And apparently predicates may consist of an infinite number of propositions, which of course is impossible to express in equations such as these. And the usual way to write the logical AND of all the propositions in a predicate is indicated using a symbol that looks like an upside down capital letter A. And you can see it right here. The symbol, which is the universal quantifier, is denoted by this upside down A. And for example, we might have an expression like this, in which we are saying for all x, P of x, and this simply stands for the logical AND of all the propositions in the predicate P. If there is a single proposition that is false, the predicate is not universally quantified. So if we take this equation here, if there's any possible proposition of x that evaluates to false, then the overall expression is false. So this formula, which you can see here, reads for all x, P of x is true. And the value of this formula is false if there is an element in X from the universe of discourse for which the proposition P of X is false. Otherwise, P of X is true. If n stands for a natural number and E of n indicates 2 times n is a non-negative even number, then E of 0, E of 1, E of 2 is a set of propositions indexed by the natural numbers. For each natural number n, there is a corresponding proposition E of n, so E is a predicate with the natural numbers as its universe of discourse. We can express a logical and, including some propositions, such as this, E of 5, and E of 3, and E of 7, and E of 1, and this formula has the value of true because each proposition is true. In fact, all of the propositions in the predicate E are true. E of n is true regardless of which natural number n stands for, because any number in the form 2 times n is a non-negative even number when n is a natural number. Therefore, there is no element in n in which the universe of discourse of the predicate E for which the proposition E of n is false. And this means that the value of the quantified formula for all n E of n is true. A quantifier converts a set of propositions, that is a predicate, into a single value, true or false. That is, a quantifier converts a predicate into a proposition. A quantified formula starts with a quantifier symbol, followed by a variable, then a period, and finally a logic formula representing a proposition. The variable, which is known as the bound variable in the formula, stands for an element in the universe of discourse. The universe of discourse is not specified directly in the formula, but the formula has no meaning unless the universe of discourse is known. Let P be a predicate. The formula for all A, P of X is false when there is at least one index X in the universe of discourse for which P of X is false. Otherwise, the universal quantification is true. If the universe of discourse is empty, there aren't any indexes at all, let alone one for which the predicate is false. Therefore, for all X, P of X is true when the universe of discourse is empty. An existential quantification is false when the universe of discourse is empty because it can only be true if there is at least one element X in the universe of discourse for which P of X is true. Any variable that is not bound is called a free variable. In the following formula, X is a bound variable and Y is a free variable. For all X, P of X, and Q of Y. In the following formula, X is the bound variable in the operand on the left-hand side of the logical OR, but a free variable on the right-hand side. And you can see that here. We have, it should be for all X, P of X, logical OR, Q of X. And so over here, on the left-hand side, we're missing the universal quantifier here. But what this is saying is that X is bound in the left-hand operand of the logical OR, but it is free in the right-hand operand of the logical OR. The only other quantifier we will use is the existential quantifier. It forms the logical OR of all the propositions in a predicate and is represented by a symbol that looks like a backwards letter E. The formula for some X, P of X, has the value true if there is an element from X from the universe of discourse for which the proposition P of X is true. Consider the equation n plus 7 equals 12. Any equation is a proposition because it is either true or false. Let's call this proposition Q of n. Q is a predicate with the natural numbers as its universe of discourse because for each natural number n, Q of n stands for a proposition. We know there is a natural number n for which equation n plus 7, 12 holds. When n equals 5, the equation holds. N is in the universe of discourse, and the proposition Q of n is true when n is equal to 5. The formula for some n, Q of n is true. The formula for all n, Q of n is false because there is a natural number n for which the proposition Q of n is false. In fact, there are many of them, but the number of these false propositions in the predicate doesn't matter in a universal quantification. One is enough. By the definition of the universal quantifier, the formula for some n, Q of n is false if there is even one element of the universe of discourse for which the proposition Q of n is false. The three-line variation of the equal sign, which you can see here, indicates that the term on the left-hand side stands for the formula on the right by definition. So we have a term followed by 3 bars, some formula, and this is the definition of a term. Here you can see we're defining Q of n as n plus 7 equals 12, and in this case Q of n stands for n plus 7 equals 12. Predicates can have more than one index. For example, the following predicate R has 2 indexes. So we have this predicate R, which has variables m and n, and then on the right-hand side of the 3 bars, we have n plus 7 equals m. And let's assume for a moment that the universe of discourse for both indexes is the natural numbers. So for each pair of natural numbers nm, Rmn stands for a proposition. The equation n plus 7 equals 12, which is either true or false. The formula for some n, R of mn, is a different proposition for each natural number m. That makes it a set of propositions indexed by the natural numbers, so it is a predicate with the natural numbers as its universe of discourse. Let's name the predicate. So if we describe S of m as for some n, R n of m, we can then substitute S of m for what appears on the right-hand side of these 3 bars. And alternatively, we can substitute this expression on the right for this expression on the left. Let's convert this predicate to a proposition by quantifying it. For all m, S of m. This is a proposition, so it is either true or false. By definition of R, S of m is true if there were no natural numbers m for which the quantification for some n, n plus 7 equals m, was false. Suppose m is the natural number 0. The proposition S of 0 says for some n, n plus 7 equals 0. There are no natural numbers n such that n plus 7 equals 0 because n would have to be negative, and all natural numbers are 0 or bigger. That makes the expression for all m S of m false. By definition, S of m stands for the formula for some n, Rn of m. So we can put that formula in place of Sm, S of m, in for all m, S of m. So the formula becomes for all m, for some n, Rn of m. And this is an existential quantification nested inside a universal quantification.